Hello there, this is Yuchen Lin, and this is my semester 3 report. And first of all, randomness only exists in context as a relative property of sequence of numbers in large set of data and patterns determine if something is random. So for example, if we play the guess a number game, where I will pick a number and you guess what it is. If I pick a 6 at the first time, you may believe that 6 was random, but if you did not know how that number was arrived at, you will have no ways of determining if it was random. If the game runs for thousands of times and I pick 6 each time, now there is a pattern where I only pick 6 for the game, and it is not random. With the help of possibilities, we can define randomness as the number of events approaching infinity. So if the possibility of each event of happening equals to 1 divided by n, where n represents the number of events, then we can say each event in the sequence is random. And for computer, we often use binary to represent a number, which means the probability of any specific C number in the sequence being equal to 1 is exactly 0.5. Or in other words, the value of each binary number in the sequence is perfectly random. If a string of binary numbers is generated meeting that requirements, it is random. And any number transformed from that string of binary numbers is also random. On the other hand, humans are bad at generating random data since we are biased and we make decisions based on personal experience. For example, the draft lottery experiments during the class demonstrated that what humans think is random is not. It's rarely happens. Okay, so the second one, both simulations and the game use randomness to represent dynamic things, interactions between objects, process, and force. So in simulations, we use randomness as a manipulable abstraction of the objects being simulated, while in game, we use randomness as a way to represent complex process that might not be critical to the game, but that lend a sense of realities, complexity, or presence. So for example, let's say we want to simulate car traffic passing by a particular location on a certain road. In this case, the particular time that a car passes this specific spot is random, unless constrained by congregation. So in order to represent this randomness, we can treat this sequence of cars as a high level of abstraction of a set of time values. This sequence would have random characteristics and those could be measured and replicated. A similar but distinct sequence could be generated. One only has the same statistical properties and thus representing a sequence of cars that would look very similar to the real one. And with randomness applied in this situation, in this simulation, it allows us to measure the traffic density or flow at some point. Determine the average gap between cars and estimate the amount of fuel being used. The randomness here serves as an abstraction of time sequence to represent the traffic. On the other hand, with similar approach, we can also simulate the traffic in a games, but with a different purpose. As a passenger in the game, the way the traffic scene looks is a critical part of the background, but may not be a primary component. When we are playing a game and trying to control a character to pass a street, if all cars move with the same speed, same space, with certain pattern, it doesn't seem real. And it may distract from the focus of the player of the game. In this case, the randomness here serves as a background features to represent the reality in the game. And for the third part, all simulations are anchored by time. Some simulations are about distinct events that happen at a particular time, and some are about things that change continuously in predictable, measurable, or observable ways over time. And where we can use just a formula with time to measure that. An event describe a discrete, identifiable change in the system, such as the arrival or departure of a bus. Events in the discrete simulations are defined by time, which determines the order of the events. A discrete simulation can be viewed as having a series of states, which can be constructed by events and time to serve as a description of the current situation of the simulations. So when we advance this time, the state of the simulation changes accordingly, and we can capture the data at a certain point. So to answer the questions like how long the custom line is now, therefore time is fundamental in occurring events in the simulations. Once we advance time, the simulation is actually running. So when we design a simulation, we not only want it to be run successfully over time, but also to represent the reality in the real world. However, reality has certain characteristics that are hard to represent convincingly. So for example, we want to simulate a realistic tree, and we can start from a seed, the force of moisture, light, temperature, chemistry. Over a great deal of simulated time, the tree can be grown. On the other hand, we can select the number and the shape of the branch for each tree at random, which much faster and doesn't require detailed knowledge of how trees grow. Randomness can be used to duplicate these results of complex real-world activities. Considering the car traffic example I mentioned in the question 2, the particular time that a car passes this specific spot is a result of a complex sequence of events that would not be likely to be known in details or repeatedly exactly. And we can use randomness to construct a high level of abstraction of a set of time values, which makes the simulation look very similar to the real one. In other words, the addition of randomness makes it possible for us to add reality to the simulation process. Okay, and the last one for my project, I'm trying to simulate a blackjack game. In some casinos, they want to use several full decks of cards in one game instead of using cutting cards to exclude some cards from after shuffling. And the player will place the cutting cards at any location as they wish to, and those cards will be moved to the end of the shoe. Then the dealer will exclude a certain number of cards from the tail, assuming that placing the cutting card at each location has same possibilities, and the game can be run thousands of times. Then this process can be defined as random for my simulations. In order to generate the random number, I will use the mass_random functions in JavaScript to generate a number between 0 to 1. Then based on the number of cards available in the shoe, I can define a max and min values that each shoe generated from the formulas, like max.random times max minus min plus min. In my case, the min value should be 1 and the max value should be total number of cards in the shoe. In addition, since I only care about the integer, I can use the mass_flow functions to get integers instead of floating numbers. Therefore, the values can be generated is between 1 and the number of cards